Hi, my name is Harold Schuch of the Department of Civil Engineering at the University of Colorado, Denver. This is the second module about levels, and this is called vertical traversing. It uses some of the concepts that were presented in the first module called automatic levels. What is vertical traversing? It is the idea of collecting sequential information with the help of measurements that are performed with an automatic level and with leveling rods. And a traverse can be open-ended or it can be closed, as in this case. What we're going to do is we're going to look at some of these measurements. We're going to look at the error levels, and we're going to look at a mean to correct those error levels with the help of an adjustment. So here again, we're going to start from a point with known elevation. We're going to advance along a sequence of turning points and come back to our starting point. The standard operating procedure for this kind of leveling along a traverse is that we first set up an instrument that is convenient so we can read both a backside and a foresight. So the backside would be at our starting point and the foresight would be towards our first turning point. Then we move the instrument to a next convenient location where we can see our turning point 1 and our desired turning point 2. And so we continue along this loop to then come back to our starting point. If our calculated elevation of the starting point as we come around the loop is different from our given elevation at the beginning, then we have a misclosure that needs to be corrected. And once we have this correction established and applied, we then can calculate the elevations of these points. To repeat something that was mentioned in the previous module, this point is called a turning point because you have to first see this rod from this direction, then you have to turn this around almost 180 degrees so you can see the rod from this direction. So this is why this is called a turning point. You turn the rod. Now, how do we collect data? Data are collected with tables that have a standard format. We can do more with these tables. We can record measurements such as backsides and foresights and point names. We can also adjust our measurements and we can calculate adjusted elevations along a loop. So then finally, what else can we do with this table? We can use this table for delivery of results to the customer. If you use a standard format, then it will be less likely for you to be asked to explain what you delivered. At the bottom of the table, you will see information that will be used at the end for adjustment and correction. Let's first use this table to collect field data and record them. We will do a complete run-through of a project from data collection through correction, adjustment, and delivery. So let's say we are in the field with an automatic level and a rod, and we are ready to take our first measurements. The first thing we have to do is at our starting point, we have a point name that we enter in the table, in the first row, in the first field. And then we set up the instrument so we can shoot a backside towards this starting point. Now we still have to record the elevation of our starting point, and we do that over here. Now we take our backside reading towards this rod, and we enter that value, the rod reading here, right underneath backside. Now, if we take the elevation of our starting point and we add the backside, we get the height of instrument. That's not something we can immediately calculate. So in other words, if we take the elevation of our starting point, we add our backside, then we have the height of instrument here. The height of instrument is another elevation. So the equation to do that is right in here. Now note that the height of instrument is entered into its separate row. Nothing else will be recorded here in this row other than this height of instrument. The next step is to turn this instrument around and take a foresight reading and record that. So we enter the name of the foresight point, which is TP1. We enter the foresight reading, which is this reading here. And if we take this height of instrument minus that foresight reading, gives us the elevation of this point. So our height of instrument minus that foresight gives us the elevation of point TP1. We can notice that height of instrument is by itself in that row that is otherwise empty. We have just completed the first readings, the first set of backsight and foresight. So this block of data will be repeated throughout this table. Every time we have a new instrument set up, we'll have a new set of 3 lines. So now we take the next instrument set up here, and we have a backsight now. This is backsight 2 towards TP1. So we have a backsight towards TP1. And because of that, we can now calculate the height of instrument. So this height of instrument equals this elevation plus the backsight reading. So this elevation plus this gives us that. Down here you have the equation. Now we turn the instrument around and take a foresight reading, and we record it here next to the name of that point, TP2. Now we have this foresight reading. All we have to do is take this height of instrument minus that foresight reading gives us the elevation of this point. So this height of instrument minus that foresight gives us the elevation of TP2. Now we move the instrument to here and take a backsight reading. Now we turn the instrument around and take a foresight reading. We now have the elevation of point TP3. Now we're going to move the instrument over here, and we're going to take a backsight reading and then a foresight reading towards our starting point. Here's our backsight reading to TP3, and then a foresight reading to BM1. We end up with an elevation that is calculated around the loop. A new elevation for TP1. And you notice that they're not the same. There is a misclosure of 7/100 of a foot. So let's see what we do next. We calculate this misclosure, this minus that, as 0.07 feet plus. Now we can use these fields here. If we add up all the backsides and we add up all the foresights and subtract this backside from this sum of foresights, then we get the same number, the same misclosure. So there's 2 ways of calculating the misclosure. One of them is this minus that, or the other one is this sum minus that sum. What is our correction? Our correction, first of all, we have 1, 2, 3, 4 instrument setups. That means we have 4 heights of instrument. So our number of heights of instrument is 4. If we take this misclosure, we change its sign to minus 0.07 to make it a correction, and divide by 4, we get our correction per height of instrument. How do we apply this? We apply this correction to these heights of instrument. Let's do that. So we apply this correction 1 times to this height of instrument to end up with this. This is the adjusted height of instrument. Then we take this height of instrument and apply twice, 2 times this correction to end up with this. Then we take this height of instrument and apply the correction 3 times to get that, and this plus 4 times the correction to get that. So now we have adjusted heights of instrument. Remember, we use these height of instruments to calculate these elevations. So now these elevations will change because these height of instrument changed. Therefore, what we will do is we will take this height of instrument minus this foresight will give us an adjusted elevation. This height of instrument minus that foresight will give us that adjusted elevation. So we don't adjust, we don't change our foresights, our measurements. We only change our calculations. And in this case, the last one is this adjusted height of instrument minus that foresight gives us that adjusted elevation. And lo and behold, we did our task properly because now our elevation as we come back to our starting point is the same as the given elevation for that point, and our misclosure has now sunk to 0. Now, this is of course going around the loop. What if we pick up other points on the side as we go around the loop? Let's say we go around the loop and from this instrument setup point, which doesn't have a name other than a height of instrument, we pick up 3 more points on the side. These are called side shots or intermediate points. You can of course have more side shots from here and from here. How are they treated in that table? Once the heights of instrument are adjusted, these measurements are inserted in their own rows corresponding to the height of instrument in question. In this case, the 4th instrument setup, the 1, 2, 3, 4. Right after the 4th height of instrument, I put in all my intermediate points. I can even give them names, which I didn't do in this case. And from these intermediate readings, which are all really foresights, I take this elevation, this height of instrument, minus that gives me that elevation. This height of instrument minus that gives me this elevation, and this minus that gives me this elevation. So I have now intermediate point elevations that are subject to the adjusted loop, the adjusted traverse. So one can use these intermediate points to pick up things that are necessary from a surveying or engineering perspective. In this case, checking if the building is level and at the right elevation. What's the elevation of this building corner? Equals this height of instrument minus this foresight, minus this IP, intermediate reading, intermediate point reading. So then we can tell our customer, yes, the building is level and at the right elevation. In closing then, this procedure is the core of all leveling applications, whether they are used to implement designs or to report on construction compliance, or what is called as-built reports. Learn it and enjoy. I hope to see you in another module. Thank you for listening.